Okay, can everybody see the slides?
Yes.
Can you see the slides? And switch off the slides?
Yes, I can see the slide.
Okay, perfect. Yeah, let's wait for one more minute. Okay, good morning, everyone. Let's get started. So first of all, apologize again that we have still need to take this Zoom lecture this Tuesday. I think if everything goes smoothly, we're gonna have a classroom teaching on this Thursday, but I will update you while Canvas. So please watch your Canvas notice. In the last lecture, we introduced the one strategy of the ensemble learning, which is called boosting. Right? So, but basically, what's the ensemble learning mean? So it says that, okay, we have a set of base learners, like base classifiers. The ensemble learning tries to smartly combine a set of base classifiers to get a stronger one. Right? That's called ensemble learning. So there are two important strategies for ensemble learning. One is called boosting, and the other is called bagging, which we're gonna focus on today. Right? But before that, we would like to quickly review the boosting strategy we discussed in the last lecture. So the basic idea of boosting is that, okay, we're gonna construct in sequentially a series of weak classifiers, right? We got some formal definition according to the computational learning theory framework, but we don't want to repeat again. So, but basically you can will those weak classifiers as ones which are just slightly better than random guess, right? You can will like your weak classifier just a little bit better than you just random toss a coin and random guess. For example, the most common used weak classifier is just decision tree with one additional level. That means decision stump, right? You just use one attribute to split on data set, and you stop growing. So the idea of the boosting is to iteratively reweight the training data, right? So at the beginning, we weight each training example equally important. Suppose you have 10 training examples, then at the beginning, each example will be just 0.1, right? And then every time, based on current data weights, we're gonna train our weight classifier. And once we got our weight classifier, right, according to the prediction error, right, we're gonna use our weight classifier to make prediction over every training example, and we know which example is correct, which example's prediction is wrong, right? So based on those weighted error, we're gonna reweight those training examples. During this reweighting procedure, we kind of increase the weight of those incorrectly predicted examples because there are mistakes, right? And then we're gonna downweight those examples that are correctly predicted by the current weight classifier. So in the next round, based on those updated weights, we retrain a weight classifier. Our goal is that, okay, for those mistakes made by the previous weight classifier, this time we want to correct our mistakes. We want to classify them correctly. And for those examples that have been correctly classified in the previous rounds, their importance are not will that much, right? So just to keep doing this until the maximum number of iterations are done. And finally, we combine those weight classifiers together, and each weight classifier has their own vote, right? So we just use each weight classifier to make prediction, multiply their votes, and we just count the total vote, which prediction has made the majority vote, and then we make our final prediction. Right? So this is the basic strategy of the boosting. So the most prevalent example is ADA boost, which I have specified how they do the reweighting each step. How do we compute the vote of the weight classifiers? Right. So all the detailed steps are listed in the algorithm table. So everyone should be able to implement your ADA boost based on, say, your decision stump. Right. So here's the quick summary of the ADA boost. So it is simple, fast, and only needs to tune one hyperparameter. That is the number of iterations, or in other words, the number of weight classifiers. And in theory, it can be used with any weak learning algorithm, although the most popular weak learner is the decision stump. We mentioned quite a few times, right? But there's also some shortcomings, right? So first, the performance really depends on the specific data set and also the choice of weak learners, and also quite sensitive to the choice of weak learners. If the weak learners are too complex, it could fail. If weak learners are too weak, it could fail as well. Right? So now we can see boosting and also ADA boosting is art to play with the weight classifiers, right? And the original motivation is that, okay, even we have a set of weight classifiers, we can still assemble them into a much stronger one. But the problem is that, okay, now the choice, how weak these classifiers are kind of like determinant, right? It's kind of like so sensitive, right? That's not very convenient, right? So people naturally ask another question: do we have other ensemble learning approaches that, okay, we do not need to carefully choose the weakness of the classifiers? Right? Can we just run our decision tree to let it grow as large as possible, as deep as possible, as wide as possible? And do I still have like smart combination approaches to improve the performance? That reduces to the second strategy, which we're gonna discuss today. It is called bagging, right? The bagging methods. So the biggest difference between bagging and boosting is that bagging actually encourages you to employ strong classifiers as base learners, right? Namely, when you run the bagging, for example, if you use decision tree as a base learner, you can run your decision tree. You can grow your decision tree as large as possible. And that's very welcome in the bagging strategy. And then you see that bagging essentially is very, very simple strategy, but it is surprisingly stable and good. Okay. So we're going to talk about the general bagging strategy and also the random forest. So any questions so far? Okay, so what is bagging? Right? So in general, it's a type of meta algorithms that combine the output of multiple classifiers. Right? So often tend to be empirically robust. So later we'll give some rigorous justification showing why bagging can give you more robust result and smaller generalization error. But here we want to give one example. In 2009, the winners of 1 million Netflix prize was a giant ensemble. So Netflix prize is this company Netflix. They have some kind of competition, data science competition. They release some kind of competition task, which are part, mostly based on their own need, right? Because they're some kind of stream media, right? They want to recommend movies, right? They want to make like a pricing strategy and so on, right? So they formulate this kind of data science problems and encourage researchers to address their problem, right? So, and the winner in 2009 turns out to be a giant ensemble. So that you can see that how ensemble is successful, right? So what is the general framework for backend algorithm? By the way, it is short for the bootstrap aggregating, right? But I think backend is more, is a kind of easier to understand. It's very intuitive. I will see. So first, suppose we are given a training set with m examples, right? And similar to AdaBoost, we choose to run like the big T iterations. And inside each iteration, the small t, we have 2 steps. So first, we're going to resample our training data. How can we do that? We just will the original training set as kind of like a, an empirical distribution. We draw m prime examples uniformly with replacement from the original training set. So I want to ask, what's the meaning of uniformly sampling with replacement? Could anyone give a hint?
It's possible to resample something multiple times.
Any thought? I thought it's a basic concept in statistics. I thought everyone should know that.
1 by m.
Can you say it louder? I can't hear you.
1 by m.
1 by m. Okay, yeah, that's one point. What's another point? So you said 1 by m is telling about uniform, right? So what's the meaning for the with replacement?
They all are identically distributed, like independent. So if you if you draw one sample, that won't affect the other sample to draw, like equally, they are equally distributed.
Yeah. Okay, thank you. Let me explain it in more details, right? So basically, with replacement means once you draw a sample, you do not exclude it from the sample space. Next time when you draw again, you still have the equal chance to draw that example. Like you have a set of balls, right? And suppose you want to draw those balls uniformly with replacement. What does it mean? It means that, okay, every time I just have equal chance to pick up any ball, right? Once I pick up the ball for example, the first ball, that doesn't mean I just throw out into some box or garbage, right? Instead, after my first sampling is done, right, I put the ball back. And next time, I still draw this many balls. I still draw from this many balls, right? So that means the first ball still has the equal chance to be drawn again. Does it make sense?
Yeah, I see. Yeah,
I
can remember.
That's the meaning of replacement. If it says without replacement, that means, okay, once the first ball is selected in this step, it will be thrown out. And next time, your sample space will be the remaining balls. You cannot draw the first ball anymore. Okay, so this meaning of the uniform with replacement meaning that, okay, every example, it can be sampled multiple times. So here I want to give a more concrete example. Okay. So suppose our data set consists of 5 examples, x1 to x5. Right? So we got the size of data set is 5, right? Suppose we set m prime to be 5. Right? So what do we mean by uniformly draw 5 examples with replacement? Right? So first time, we know that every example, every of these 5 examples has equal chance to be selected. Right? So first time, say we select x1. But next time, right, we put x1 back in the original data set, and then we sample them again. So then x1 still has equal chance 1/5 to be selected. So suppose this time we still selected x1, right? And then next time we might select x2, next time x4, and the 5th time maybe x2 again. Right? So this now we have reached the cap, right? M prime equals to 5. So we finished drawing M prime examples uniformly with replacement from the training set. Does it make sense? Everyone is good, right? And here's another example, right? Suppose for another iteration, we draw another 5 examples uniformly with replacement. What does it mean? So the first time it might select x2, but doesn't. But we still put x2 back in the original data set. For the next sample, we're gonna select another example, right? Equally chance, right? But suppose this time we still select x2, right? And third time we select x3, and first time we select x4, and fifth time we select x5, right? This is the second round, right? In the third round, we might select x1, x3, x5, x5, and x4. Okay. So under the procedure, like uniformly sampling with replacement, implies that we might sample duplicate examples in our data set. Can you see it again? Do you have any question? Or someone saying something? Okay, so hopefully everyone is not confused at this point, right? If we have m prime equals to m, meaning that our resample data set has the same size as the original data set, then this resample data set is called a bootstrap sample. So, well, this is kind of like a term in statistics. It's called bootstrap, and if you learn some statistics course before, you might also discuss another concept called jackknife. But this is not of our scope. But here we just want to give you a concept that if you want to use this uniform sampling with replacement to sample the same number of training examples from the original training set, then your sampled training set or sample data set is called a bootstrap of the original data set. Okay, so once we have resampled a data set, okay, let me read out someone's question. What happens if the sample we're picking does not resemble the sample space? For example, say pick up a red ball from sample space 0. Okay, that's a good question. So here the basic assumption is here. So first, our original training data is sampled from some underlying data distribution, right? So our original training data samples from from some underlying data distribution. This is what we expect, right? And when you do the resample, you are using the original training set to create a empirical distribution, right? So basically, you can view like it's kind of histogram, right? And now you generate new samples according to this empirical distribution. Okay? So if you just marginalize out this empirical distribution according to the underlying data distribution, you see that actually your resample data distribution still follow the underlying data distribution. So statistically speaking, it won't alter the underlying distribution which generates those examples. So you won't need to worry about that. That's why bootstrapping is kind of popular in statistics. It's kind of like, okay, I'm kind of like resample the data, but I don't need to really collect new examples. Right? It's just based on the original, based on the first collection of the train set. Does it make sense?
Yes, Professor.
Can you say again?
Yeah, I got it. Thanks.
Okay. Great. So, but here, I mean, from practical perspective, I want to emphasize that you should be careful, because using this bootstrap, it means that your resampled examples might have duplications. Okay. So now, suppose we have collected such a resample data set. On this data set, we're going to train a classifier, which we denote by CI. So you can use any strong classifiers, strong learning algorithms to train on this data set to get classified. So we just do this. We repeat this for big T iterations. Then we have a collection of big T classifiers. Then we construct a final classifier by taking votes from every base classifier. So one point we want to emphasize that you can see that in each iteration, what we're doing actually is independent of what we have done for other iterations. Right? So every time we just draw M prime samples uniformly with displacement, this drawing procedure is kind of independent of the other resampling procedure. Okay. And then we train our classifier on this training set. Okay. So that means if you run bagging, you can run it in parallel. This is kind of an advantage over bootstrapping, right? It's a boost or boosting, right? Because a boost, you have to run it sequentially, because you need to, based upon the current classifier, the weight classifiers, weighted error to determine the weights of the examples in the next iteration, right? So it must be run sequentially, right? But here, bagging, we don't need it. We can execute each iteration like in parallel. Okay. Any questions so far?
So is there any chance like this M prime may be same, like 2 M prime may be the same, equally drawn, like X1,
Yeah,
X2, X3?
Yeah, that's a very good point. Yeah, there is some chance on that. Although the chance is relatively small, but still there are still some chance.
Okay, so the decision tree will also be the same, like whatever.
Of course.
Decision.
Yeah,
Okay.
yeah. If you resample data set, if 2 resample data sets are exactly the same, of course you run decision trees, that will be the same.
Okay, got it.
Yeah, that's a problem. Of course, there's no perfect algorithm. But later we'll talk about random forest. You see that even in the random forest setting, even your resampled data sets are exactly the same. There's still low chance that your 2 trees will be identical.
Oh.
For that case, we will need to modify your tree construction a little bit to increase the to increase the chance that 2 trees are completely different. We'll reach to that point later. Okay,
got it.
Okay. So now, suppose we have run this procedure, right? We got a collection of the classifiers. Now, how do we combine them? Like, how do we construct a final classifier by taking votes from the base classifiers? So if we're doing regression, meaning that, okay, your prediction is kind of continuous value, it's very simple, just do average. Like suppose you got two base regressors. Now, given new input, right? We use each base regressor to make a prediction, which is continuous. Now we just average them together. This is our backend prediction, right? So if our task is classification, then we just count how many base classifiers produce positive, how many negative, and then we look at eventually which label gives more vote, right? Suppose 7 base classifiers predicted as positive, only 3 predicted as negative, and of course we're gonna finally predict the positive label. Okay. So any question so far about the aggregating strategy? It's really straightforward. Okay. So here I want to emphasize that the multiple versions of those base classifiers, right, are constructed by making bootstrap replicates. Right? So that means in practice, we usually choose m prime equals to m, meaning that we resample the data set of the same size, exactly the same size of the original training set. Right? So the idea is that we're going to use samples of the data with repetition. And then test on real and simulated data sets using classification and regression trees and subset selection in linear regression shows that bagging can give substantial gains in accuracy. So what kind of base learners or base classifiers are appropriate for bagging strategy? Right? So here, one practical guidance is that if your training, your base learner is kind of sensitive to the perturbation of the training set, meaning that you vary the training set a little bit, like say change 3 or 4 examples, it can have a significant change on the finally learned model. Then bagging can improve the accuracy by improving the stability of the prediction. Okay, someone asked in the chat box saying, so will the final prediction be in hypothesis space? For ADA boost, it is not in hypothesis space, right? That depends how you define your hypothesis space, right? So if you're saying, okay, our hypothesis space is restricted to the base learner, of course, it won't, right? We kind of like extend the hypothesis space, like for ADA boost, because you can imagine our final hypothesis is a linear combination of base hypothesis, right? For the base classifiers, the weight classifiers. So if you can imagine an extreme case, right? 1 vote is 1, the other votes are simply 0. Then your ADA boost final hypothesis will be reduced to 1 simple or weak hypothesis. Right? So that means the total hypothesis after ensemble learning is actually a superset of the hypothesis of each weak classifier. Does it make sense? Yeah. Okay. Any other question regarding understanding of the backend strategy? I think it's relatively straightforward. Okay, is everyone comfortable? Okay, so let's proceed. Right. So here I just want to give a kind of like brief summary of the general strategy for bagging, right? When we combine with decision trees. So again, decision tree is the most popular base learner used in bagging, right? When you look into some machine learning libraries, I think right now is has tried several off-the-shelf machine learning libraries. Like if you look at ensemble learning, you see bagging, random forest, they're all based on decision trees, right? So when we combine decision trees, here's the way we train a bagging of decision trees. So in each iteration, we're gonna draw a bootstrap sample set of data, right? So we in total draw big T bootstrap sample sets of the data. For each bootstrap sample set, we're going to train a decision tree. So finally, we're going to have a collection of big T trees. Right? And then once we collect these big T trees, to make the final prediction, we just average the prediction made by each tree. Right? So suppose we got 1, 2, 3, like about 10 trees here. Right? Each tree has their own prediction. This is for the regression case. Just take the average. Of course, if you are doing the classification, you just count the vote of each label predicted by all the decision trees. Right? Pick up the one who has the largest vote. So here's the pseudocode to implement the bagged decision trees. Right? So suppose we're given a training set with M examples. Right? We conduct big T iterations. As we mentioned, these big T iterations can be done in parallel. That's some kind of advantage over boosting algorithms. So in each iteration, we draw M examples uniformly with replacement from the training set. Namely, we collect a bootstrap sample of the original set. So here, the resample data set has the same size as the original training set. We denote it by xt and yt. Xt are training inputs, and yt are the test output. Right? Then based on this xt, yt, we learn a decision tree city. Right? We use an ID theory algorithm, which we have discussed in our class, or CART, or some others. So we know that a CART is for regression tree, right? And you can choose the information gain you like. For example, the gene indexing, the information gain, and also based on entropy, and also a majority error gain. So repeat this procedure for big T times. We have collected big T decision trees, and when we make a final prediction, we'll either vote or average big T predictions for classification or regression respectively. So any question regarding the algorithm steps? Okay, so from this algorithm procedure, we see the bagged decision trees are really looks like it's really simple, right? As long as you have like a well implemented decision tree learning algorithm, you just repeat this procedure, right? So your additional step will be just draw a bootstrap sample set, right? Which is pretty straightforward. And then when we do the prediction, it's very intuitive, just to average or do the vote, right? But in practice, I mean, numerous practical examples have shown that this strategy is really, really effective, right? So that naturally brings up a question, right? Why? Right? Why such a simple strategy can improve the performance so well, right? So here we want to give a kind of rigorous analysis, and you see that even use some like simple statistic concepts and do some kind of derivation, it can still reflect the nature of those learning algorithms. So so why it works? So intuitively, we can imagine that, okay, we're gonna train a set of predictors, right, rather than just one. So when you do the average, intuitively, the average prediction will be more reliable and robust. Right? So we want to can you say it again? Excuse me, what's your question? Okay, so if you have any question, just interrupt me and let me know. Okay, or type in the chart. So here we want to give a brief sketch of the theoretical justification. So we denote the training data set by D. and the learned predictor by H. So H could be your learned decision tree, right? And also the ground truth function, which gives the ground truth labels by F. So we were looking at the prediction made for a new test example X star, right? Let's assume this X star is fixed and constant, right? We just look at how the prediction made by the baggage trees and each single tree, right, on X star, right? So let us analyze the squared error averaged over all possible training sets. So for this particular training set, say D1, you train a classifier, you train a decision tree, you get a predictor at H, you make a prediction. And here we assume we're predicting continued value, right? So we got a square error, right? Fx star subtracted by H of star and take square. So now let us consider, like, because if you want to look at how well your learning algorithm is, one particular training set won't be sufficient. You want to look at, okay, hello? Are you asking some questions? Hello?
I think Kunal just isn't muted. So if you want to mute him, that might save some interruptions.
Yes, I believe so.
Oh, okay. Yeah, I'm sorry. I cannot mute anyone, although I'm the host of the meeting. But please,
Yeah,
mhm.
I requested him personally in the individual chat to mute him. So yeah, maybe that works.
Yeah, I've also done that.
Okay.
Okay. Thank you. Thank you. Yeah, appreciate it. Yeah. So if everyone, if you need to talk to anybody else, please mute yourself so that other students won't be affected. Okay. Just give me a second on the case. Okay. So again, let us analyze the square error average all the possible training set, because one training set won't reflect how well your learner is, right? So we want to take expectation over the possible training set. Remember, the training data is generated by some underlying data distribution. So they are essentially random variables, right? So we're going to take an expectation of the squared error in predicting this particular example X star with respect to the training data. Okay. So any question regarding this term we want to analyze? Okay. So now let's look at what kind of structure can we find from this expected square error. So we're going to use some commonly used trick in statistics. So inside this difference, right, fx star subtracted by the prediction h of x star. So someone asked, what does biased variance decomposition? We'll reach to that point in a minute. Okay. So we'll first subtract fx star by some expectation and plus some expectation. So you can see that this doesn't change the whole difference at all, right? Because we subtract, we are subtracted by something and then added by the same quantity, right? So actually canceled out, right? So it doesn't change the result at all. Right? So the quantity we are subtracted and plus is expectation of the prediction at x star. Right? So that basically says we just look at when we vary the training data set D under each training set, we train our classifier we use that classifier to make prediction, right? Which is to take the average of this prediction along with different training set. Okay? Of course, this one would not be a random variable because we have already take the expectation. Okay? So we subtract the ground truth prediction fx
Question
star
for you.
by expected.
Professor, I have a question.
Um,
Could you please clarify the difference between x to the star and x star?
oh, sorry, this is a typo. Just x. This is just x to the star.
So those are all exponent stars.
Yeah, they're all x star. Yeah, they're all
Okay,
x
thank
star.
you.
Okay. Any other question regarding notations? I apologize for this typos. Okay, so so now what we can do, right? So we have this 4 terms put inside a square, right? So now we can expand this square. So we got this difference, take the square, and this difference, take the square, and then a cross term, right? And of course, in outside, we're gonna take expectation with respect to the training data distribution. Okay. So now the first term will be, okay, the difference between the ground truth label of x star and on average, what is your learned classifier's prediction on x star, right? Again, this is x star, right? X to the power of star, okay. And the second term is that expectation of your prediction with respect to all kinds of training set subtracted by your prediction made on a particular train on a particular data set. Right? And then take square. And outside you take expectation. So now I want to ask, what does this term mean? Any thought?
Is that similar to like a expectation for of error, acceptable error?
That actually is about the first term, right? So the first term is saying, okay, the error of you take all kinds of training set to train a classifier and make prediction, right? And this
It's
actually
kind
has
of like
nothing to do with error, right? What?
it's a measure of how much the prediction made by a particular hypothesis function varies from the average of all the predictions made by the
Yeah.
hypothesis.
Yeah, exactly. Can you just use one word to summarize your meaning?
The variance.
Variance.
Yes, exactly, right? That's the definition of variance. That's definitely variance, right? Remember, h of x star itself is a random variable. Right? It depends on the training set. Right? Training set 1, you get prediction, say 0.1, right? For training set 2, you got prediction 0.2, right? So if you take the average of your prediction based on the classifier train or all kinds of training set, that is this term, right? Now you subtract your expectation by a prediction, take the square and take expectation. Again, this is definition, exact definition of the variance. Right? And also, you can see that this variance actually has nothing to do with the ground truth label. This is ground truth label. This guy is simply the nature of the is the nature of the classifier itself. Right? Okay, let us look at the third term. Right? So what's the value of third term? Any thought?
Expected value of the error.
Expected, yeah, okay. But what's the but do you see what's the value of this term? Any thought? Yeah, it's simply 0. Why? Yeah, let us analyze a little bit, right? So first, f of x star is not a random variable, right? X star is fixed, right? And f of x star is a ground truth label on that. It won't be random, right? And this guy expected a prediction with respect to all kinds of training set. It's not a random variable as well, right? So you can see that this parenthesis, right? The value inside this parenthesis is actually constant. Right? You can move out of this whole expectation outside. Right? Then the remaining thing is that you're going to take expectation of this, the second parenthesis. Right? And this guy, again, is constant. So that means you can put the expectation onto h of x star. Right? Once you got expectation here, you got expectation here, they will be the same, right? Their difference will be 0. Right? This is a very common used trick in statistical analysis, right? By subtracting some terms and adding some terms, and you expand the square term, you usually can cancel the cross terms, because the cross term, once they take expectation, they're simply 0. Any questions so far? Everyone's good, right? Okay, so now we only have 2 terms left, right? Which is here and here, right? So the first term is expected square error of the prediction from the expected prediction, right? From the ground truth and expected prediction. Again, because f of x star is constant, right? They're not random variables, and expected prediction, right? Which you have already take expectation with respect to all kinds of different training set. So this is not a random variable again. So you don't need necessarily to take expectation, because this whole thing inside expectation is already a constant, right? So we can get rid of this expectation. So the first term becomes the square difference between the ground truth and your expected prediction under a variety of training set. And the second one, as we just discussed, it is essentially a variance of your prediction under different training set. Right? So the first term we call bias. The second term we call variance. That's where this so-called bias plus variance decomposition come from. So any questions so far? Yeah, if you feel like a little bit over complex for this derivation, don't worry. After the class, you just sit down and go through these formulas and think about why this cross term is simply 0, and the meaning of this term and this term. You get it. Right? This is just nothing but a trick of doing a square expansion. Right? So the most important meaning in this bias variance decomposition lies on how we will the complexity of the machine learning models. So let us consider, suppose your model is complex, meaning that it is very, very expressive. For example, we are running a decision tree. We can let it grow as large as possible until it kind of like will fit all the training examples. Then we know that, okay, for nearly every training examples, it can always try its best to fit all the training examples. So you can imagine a little bit change of the training set will kind of alter the tree structure a lot, right? So as a consequence, the variance of the tree prediction will be quite big, right? On the other hand, because the tree is so powerful, right? The strong classifier is so powerful. Every time, whenever training set you're given, it tries to fit the training data well. So we can imagine for all kinds of training set sampled from same underlying data distribution, it fits the training data well. So it fits or predicts the future test example, which generated from the same data distribution. On average, it will predict well as well. Right? That means the bias is quite small. So we can see that the complex models usually will lead to large variance. Why? Because to better fit the training data, right? A little bit change of training data will cause a large change of the model itself, so that the final prediction, so it has a large variance. But it has benefit because they fit the training data so well, so their bias is small. On the other hand, if our model is quite simple, like just like linear models we're going to discuss later, right? So this model is quite robust. That means if you change the examples just a little bit, it won't change much, right? The model itself won't change much. So the variance will be pretty small. At the same time, because it won't fit the training data so well, right? So the bias will be large. So that's a typical bias and variance trade-off for different types of machine learning models. Right? So it's not the case that, okay, the more complex model you have, the better generalization error you will have, or the simplest model you have, the better generalization error you will have. Instead, you're going to pick up the best trade-off between the two. Right? Your model couldn't be too complicated because of the variance can be too large. Right? On the other hand, if the model is too simple, kind of underfit data, the large bias kind of dominates the generalization error. It won't give you the overall good performance as well. So any questions so far? Does everyone feel comfortable?
Yes.
Okay, so we can see that from just these 3 lines of mathematical derivation actually reflects a very, very important structure which applies to almost all the machine learning methods. Right? So this is a well-known result, bias and variance trade-off, and also this it explains why in our machine learning practice we always try to like put some regularization term to control the model complexity to find a good trade-off. It's not like, okay, I'm only focusing on fitting data, right? I fit data as good as possible, like to make the bias as small as possible, because in the overall generalization error, the variance takes a important role as well. So now we want to use this bias and variance decomposition to explain why bagging works. So we still use bagged tree as an example, right? So as we mentioned, if we use decision tree, we allow it to grow to arbitrarily large, right? That means the decision tree tends to overfit the data, so it has a small bias, right? Because it fits the data so well, right? But it has a large variance. We can imagine if you just swap into a new swapping a new training example, the tree structure might vary much, right? But now, suppose we learn a set of bagged trees. And our prediction is just the average of those trees. Right? So the bias doesn't change, right? Because you take an average of you take an average of say h1 x star, h2 x star until h say 10 x star, you take expectation, right? And it doesn't change. It doesn't change the average value. Like if you have a 10 independent identically distributed random variables, right? You take the average, it doesn't change the mean at all. So the bias term doesn't change. But how about the variance term? Any thought? When we average a set of random variables, what will happen to the variance? Any thought?
The decrease?
Yes, right? So let me write down something. Okay, let me use a pen, right? Let's suppose we have like x1 to say x10. Okay, those are IID. Of course, in practice, we're not assuming those trees are IID, but let us assume an ideal case where those x1 to x10 are just the 10 predictions made by 10 decision trees, right? If they are IID, then you take their average. So 1 over times from x1 to x10, right? What's the variance of this guy? What's the variance of this guy?
Variance over n.
Yeah, the variance will be, it's not over square root of 10, right?
I thought the variance was over n and the standard deviation was over square root of n.
Oh, yeah. Oh, yeah, you're right. Okay, over 10. Okay. Yeah. So you can see that if those for independent random variables, if you take the average, the variance is reduced by a scale of the number of the variables you average, right? It's a significant reduction, right? So now we can see the benefit, right? If we train a bag of trees, right? We take the average as our prediction if we do the analyze, right? So the bias term doesn't change because you take an average of those variables that take expectation doesn't change, right? However, your variance term is now largely reduced. So your overall expected error will be largely reduced, right? That's why the bagging can work really well, right? Because it maintains the same level of the bias of the strong decision trees or strong classifiers, which can be relatively small. At the same time, it can significantly reduce the variance. So overall, you get a small expected error.
So is this the application of the central limit theorem to selecting good decision trees?
Not yet. We haven't gone that far, because if you're talking about central limit theory, you're talking about the symptotic convergence. Like you have a set of average variables is symptotically it will follow some Gaussian distribution. We're not talking about that far. We just want to say, okay, when you average a set of predictions, you are reducing the variance of those predictions. That's why you can overall reduce the expected error or generalization error. Does it make sense? Is everyone comfortable with that?
Is
Yes.
there any chance we're going to see this in practice?
What?
Can we see a concrete example of this kind of decision tree selection?
In our homework 2, which we're going to release, I think on Thursday, you will be asked to look at the bias variance. You will see exactly the bias term doesn't change much, but the variance can be reduced a lot by running like decision trees on say, the bank data set or the car data set, you'll see that.
Great, thank you.
And then you'll see the overall generalization error here is smaller. And by this bias variance decomposition, you'll see, oh, looks like the bias term doesn't change, right? Or has tiny change, but the really reduction is coming from the variance term. Will be consistent with our analysis. Any other question? Okay, great. But here we use some like over ideal examples, like suppose x1 to x10 are independent and identical distributed, right? But in practice, because we're generating the bootstrap samples, right? And those bootstrap samples can overlap. So rigorously speaking, those tree predictions are not totally independent. They're correlated. So that means if you average them, you take the variance, the reduction of variance is not as that large as you assuming them they are independent, but they're still empirically often a big reduction. So our analysis, let me use the laser point again, right? So our analysis for simplicity, we just talk about the continuous prediction, right? The regression problem. But for other types of error, like 0-1 error, meaning binary classification error, we still have a bias variance decomposition structure, right? But here we don't have time to cover that. But here we list the reference, which published about 20 years ago. It's a very classical paper. If you're interested, you can take a look at for the 0-1 loss, how the bias and variance decomposition is derived. Okay, so now want to talk about some practical problems of baggage trees. I can imagine you have a small set of attributes or features are strongly indicative. Okay? So the consequence is that no matter how you generate the bootstrap sample set, right, it is always the case that this small set of attributes are selected. Then the consequence is that, okay, all those baggage trees are kind of very, very similar. Right? They're strongly correlated. Then your variance reduction will be very, very limited. Right? So imagine you got x1, right? You got x1 random variable. You got random variable x1 as your prediction, right? Your second prediction is still x1. The third prediction is still x1, right? Your 10th prediction is still x1. If you take the average, it's still x1, right? The variance doesn't change at all. It's still the variance of x1 itself. So in this case, even you use baggage trees, you train a set of baggage trees to take an average, that won't give you a significant reduction of the variance. That won't give you a good improvement. So how can we address this problem? So we're going to introduce baggage trees plus, which is also called random forest. So how do random forest differ from the standard baggage trees? It just add one more step to try to uncorrelate those decision trees in different iterations as much as possible. How can we do that? So all the other steps are almost the same, right? The only difference is that when we construct a decision tree, right, every time we're gonna randomly draw a subset of available attributes, right? And then we pick up the attributes from this randomly selected attribute set to split on the data set.
क्या नहीं बट लोग लगा तेरी क्लास नहीं है अभी कर रहे फिर
Hello?
अटेंड नहीं करूं
Yeah, if hi, if you guys are talking about something else, please mute yourself. We can hear that.
Yeah.
Any question? Okay, So now let us look at the algorithm table or the pseudocode to implement random forest. So the framework is kind of similar to the baggage trees, standard baggage trees, right? So we are given a training set with M examples, and we denote our feature set by big F. Right? So now we repeat big T iterations. In each iteration, we draw M examples uniformly with replacement from the training set. Namely, we construct a bootstrap sample denoted by xt and yt. Right? Now, we're going to call the so-called random tree learner to construct decision tree on xt and yt. Okay? So this random tree learner procedure is a slight modification of the ID3 algorithm we discussed. Okay? What's the slight modification? Okay? So it still uses the same kind of recursive partitioning tree, subtree creation and expansion procedure, exactly the same. The only difference is that before we select the attribute, based upon the current attribute set A, right, we're going to first randomly sample a very small subset of A. We denote them by G. Right? So the size of G is far less than size of A. Right? And then we only look at the attributes in G. We select the best attribute in G to perform the split. Of course, the selection is based on all kinds of gains we have discussed, like information gain, entropy, Gini index, and majority error. Then we use this selected attribute to split on data set to create new tree branches, and then we recursively call this tree construction algorithm itself, right? So it will be the new subset, and also we have A with the selected attribute removed. We call it again, right? So you can imagine in the next calling and tree construction procedure on the available attribute set, we're going to first sample a small subset. From that subset, we rank the attributes in that subset and then pick up the best one. I will continue this until the tree construction is done. So now I want to ask, there is just one line of code to do this slight modification, right? What's the benefit of this slight modification? Any thought? Any idea?
So it makes the, like, if we choose the same attribute, the tree will be different.
Yeah. This one is this line of code tries to increase the diversity of the tree structure. Right? So even on the same data set, because every time your range of attributes are randomly determined, right? You first randomly sample a small subset of attributes. You only pick up the best attribute from that small subset. So even on the same data set, you can imagine at every step, the selected attribute to split on the data set can be very different. Then the whole tree structure will be different. Right? Those different tree structures will have a very uncorrelated predictions, so that when we average them together, we can effectively reduce the variance. Yeah, I saw someone said, okay, we encourage the trees to be different. Exactly. Right. Any question? Yeah, that's the major motivation, right? So you can see that random forest differs from the standard baggage trees just in the tree construction procedure. Where in the tree construction procedure, what you do is, okay, before you do the node splitting, you're not going through the whole available attribute set. You're going to first randomly select a subset of attributes from A. And in this subset, we're going to pick up the best attribute, right? So the benefit is that this randomness can dramatically increase the diversity of trees, right? Even on the same data set, right? That's the extreme case, even on the same data set, because every time you random choose the attribute range beforehand, right? So if you run it twice, it will end up very different two trees, right? And in this way,
Is there a particular scale where this becomes effective? Because it seems like with most of the data sets that we've used, we've only had a handful of attributes.
That's a good question. So random forests are particularly used for when you have many attributes. If your attributes, like you only have 5 attributes, well, even you do some random selection, random range, and specify that this range is still quite small, right? It still have a chance to overlap. So in practice, when you have a lot of attributes, and this random forest is very, very effective. Does it make sense?
Yes, thank you.
Any other question?
Yeah.
Sorry.
Go ahead, yeah.
Yeah, so I want to ask a question, like this design, is it also benefit to reduce the training time? Because like previously have so many attributes, but currently has kind of smaller number of attributes.
Yeah, of course.
Okay, thank you.
Can make the training more efficient, but this is not the major benefit, because the tree construction in practice is usually very, very efficient. People are most worried about, okay, when you do this baggage trees, how do you effectively reduce the variance? But as you said, if you reduce the range of the attributes to select, of course, it can reduce the training time as well. Yeah. Other question?
Yeah, I just wanted to clarify. You said you were using bagging as kind of a way to reduce the variance, but then you used the example of, all right, what if the variance is already low for just like a standard kind of tree model? So if the variance was already low, wouldn't it be like a good predictor?
Yeah, of course.
Good.
Like I would say, like for complex models, right? For expressive models, the dominant terms will be variance, not the bias. Bias you can view like very small, but the variance term actually dominates the whole generalization error. So in that case, we would like to effectively reduce variance, because reducing the variance means that you're going to effectively reduce the whole generalization error, right? But you're saying, okay, what if my bias is small and my variance is also very small? And then it seems not necessary to do bagging. Yeah, that's of course we agree, but in practice, it's often not that case.
Gotcha.
Yeah.
Okay, thank you.
Other question? Okay, so this is very important, because you'll be asked to implement your random forest, and just be careful to make your random forest effective. Right? You can observe the difference is that in your ID3 algorithm, you should modify ID3 algorithm a little bit, right? Before you rank your attributes according to some information gain. You need to first randomly select a small subset and just rank attributes in that small subset. That's the key to the success of random forest. Okay. So now we wrap up the ensemble learning. So what I'm saying so far? So we introduced the idea of boosting, and which essentially turns the weak learnability to strong learnability. Right. So the most prevalent algorithm is called ADA boost. Everyone should be able to implement ADA boost plus decision stumps. Then we introduced the bagging method. The standard bagging and also the random forest, which further increase the diversity of decision trees, and so to uncorrelate the predictions and reduce the variance. Okay, so now we got 5 more minutes. Let us have a quick start of the quick start of the linear models. Can you see the slides?
Yes.
Okay, great. So our next big topic will be linear models. So I will discuss a variety of linear model learning algorithms and what's the idea behind that. So maybe linear models are simple from your first intuition, but it actually is the basis for many more powerful and more expressive classifiers, especially when we introduce the kernel trick. You can see that we can extend linear classifiers to be highly nonlinear and expressive models. Before that, we want to checkpoint, right? Want to look at a bigger picture. So far, we're still talking about supervised learning. We have instance space, we have label space, we have hypothesis space, and we fit the label data to our learning algorithm. A learning algorithm search over a hypothesis space. We return a learned model or hypothesis. Then we use our learned hypothesis to make prediction. So we have saying quite a few different learners, like decision trees, ADA boosting, bagging, and random forest, and so on. And also, we talk about several fundamental concepts like overfitting, like pack learnability. Right? So far, any question? Okay, so from the linear classifiers, we're going to first introduce the definition of linear classifiers. So you'll see that under the same definition, right, we have different types of learning algorithms like perceptron, like support vector machines, like naive Bayes, logistic regression, and so on. Right? And then we want to discuss what functions do linear classifiers express. Right? What's the boundary of the expressivity of linear classifiers? Then we will start with least square method for regression. So it's kind of linear regression model. So if you have taken some statistical class before, you might have already seen this. But here we want to emphasize the practical perspective, namely how do you develop efficient algorithms to fulfill the least square regression. Right? We're going to introduce the idea of gradient descent and also the stochastic gradient descent. So first, I would like to introduce the definition of linear classifiers, and also what is the geometrical geometry of linear classifiers is very interesting. And also this geometry definition is very, very important for us to understand support vector machines, which we're gonna spend quite a large amount of time talking about that. Right? And also we'll talk about some notational simplification to represent linear classifiers. So first, suppose we are given a training set like this, right? So suppose you want to train a classifier to separate out the blue circles from the red triangles. Right? Which is the best classifier? You might think about, okay, let me draw a curve, right? I can draw a vivid curve A, which kind of like perfectly separate out every blue circle from every red triangle. Right? But I can also use a very rough classifier. It's just a line, right? A line B. You can see that it kind of roughly separate the two types of examples, right? But it cannot guarantee, for example, this example and this example, these examples are seems misclassified. Right? So now I want to ask, which one do you think is better?
The line,
Why is the line better?
the curve might not generalize. It might overfit.
Yes, exactly, right? So if we think about the overfitting concept we discussed, right? If this data set, unfortunately, has already been corrupted by some noises, then this beautiful vivid curve A actually might not be a good choice. Like, for example, if some examples of like these examples and all these examples are some kind of corrupted, right? They're supposed to be triangle, and this is supposed to be the this is supposed to be the circle, right? So you're affected by this random corrected examples. You have this curve. Then if you have a new example, say a blue circle here and a right triangle here, your curve A classifier will make wrong predictions, right? It can misclassify this one as triangle, misclassify this one as a blue circle. However, if you use line, right? So although this line B doesn't necessarily give 100% fitting of the training set, it can avoid or reduce the influence made by those noises, right? So for the same cases here and here, here and here, your line B classifier will give correct prediction. That's why simple classifiers are not like people will it as useless as toys. Actually, they're also very, very useful, especially they are robust to the noises and mistakes in practice, right? And we can have the similar argument for regression, right? If we want to predict values of the training data, right? And we can choose to use a very delicate curve A to give a 0 regression error. But of course, if those examples have already been corrected by some noises, then your prediction is not good, right? The generalization won't be good. And instead, if we use a line to fit those data points instead, right? Although we won't give you a 0 training error, but it can reduce the noise, the bad effect of noise as much as possible, right? So in the future example, suppose you got a example like here, right? Of course, your line B predictor will give better error than your curve A. Right? So that's one motivation of introducing this linear models. Okay, so we're gonna start the detailed discussion of linear classifiers in next week. Okay, let's stop here today.
Thank you very much. Hope to see
Thanks.
you Thursday.
Yeah.
Thanks, Prof.
Thanks.
Bobby.